So this is our June scientific machine learning seminar. And our speaker today is, very distinguished speaker. He is the first author of several influential papers in scientific machine learning. He is the first author of the pink paper and the hidden physics paper also, and several others influential papers. He is currently an assistant professor of applied mathematics at the University of Colorado, Boulder. And he received his PhD in applied math and statistics and scientific computation from University of Maryland, College Park. He then moved to Brown University to carry out his postdoc research in the Division of Applied Mathematics under George Karniadakis. And then he worked at NVIDIA in Silicon Valley, and then he moved to Boulder. So his expertise is in probabilistic machine learning, deep learning, data-driven scientific computing. And he has been involved in the design of learning machines that are physically informed to extract patterns from high-dimensional data in several different areas. So we are really happy to have you, Maziar, and the floor is yours.
Well, thank you very much for the nice introduction, and thank you for the invitation, and thank you everybody for being here today. What I'm going to be talking today is actually a series of papers. On some of them, I'm going to go faster. On some others, I'm going to slow down a little bit. So at any time, if you want to ask questions, you can unmute yourself, ask, or stop me. The idea is that you want to marry data and equations. For instance, on the figure on the left, you have external data for external flow. And on the figure on the right, you have internal flow. Data could be in the form of a spreadsheet. For instance, it could be Excel or .csv. And you can have, for instance, 6 columns. At what time the particle was injected, when it was injected, where was it? Its X and Y locations. What time is it now? And what location the particle is at currently. That's your data. And from that data, assuming that the Navier-Stokes equations are correct, you want to back calculate the velocity and the pressure fields. This is external flow. For internal flow, the data that you see is supposed to simulate the behavior that you observe when you go to a radiologist and they're going to do 4D MRI or CT scan. This is the geometry of the aneurysm of a patient. The aneurysm is behind the left eye. And assuming that Navier-Stokes equations are correct for blood flow, we can back calculate the velocity field, the streamlines, the color coded by the pressure, and the shear stress on the wall of the aneurysm. And perhaps this is more information for the doctors of how severe that aneurysm is. So this was an overview of the talk, and I'm going to go into more details in the next few slides. And this is going to be mostly mathematical details, not too much math, but enough to justify why we are doing what we are doing. What I'm not going to be talking about today is about image classification or natural language processing or generative adversarial neural networks. I have actually a course. It's a 2-semester long course during fall and spring semester. I open sourced the course material recently online. So if you're interested in those sorts of topics, you can refer to that link. But why am I including this slide here? The idea is that even in our convolutions and even in our images, there is physics. For instance, if you take this car and shift it to the left or to the right or up or down, it is still gonna be classified as a car. And one of the reasons that convolutional neural networks are successful is because of the inductive bias or physics encoded in their structure. So they are stationary, locally translation invariant. Similar thing happens for language because of its sequential nature. People started with recurrent neural networks, but then recently, because you have a lot of data in natural language processing, basically there is 20 terabytes of data being generated each month on the internet. So there is less need for more inductive bias in our models, and that's why people are moving towards transformers or even fully connected networks. And a similar story happens for generative adversarial neural networks when you are modeling the underlying probability distribution of a high dimensional data set. And images are high dimensional because each pixel has 3 dimensions and you have a lot of pixels. But in scientific computing, we have less data. We have definitely less than 20 terabytes of data being generated each month. So we have much fewer data. So we have to try to be as data efficient as possible. So the idea is that we want to make neural networks data efficient. I'm going to start with an introduction to neural networks, but I'm going to approach it from a scientific computing perspective. Like any other machine learning framework, you have 4 components. You have data, you have prior, you have training, and you have prediction. The data throughout this talk is very simple. It's a regression data. So you have yi is equal to f of xi plus some noise. And your noise, you can model it with normal distribution with mean 0 and variance sigma squared. Let's say this is our assumption. If you put everything in vector notation, you're going to get y is equal to f of x plus epsilon. And y is going to be a vector of the size of your data. So it's going to have n. And neural networks, we know that they are really good at working with a big data. So n, we can assume, is really big. But the idea of this talk is we want to make n smaller by introducing more physics. The entire idea of putting a prior is about modeling this function f, writing a model for function f. And if we were doing scientific computing, we would say, okay, we're going to pick a bunch of basis functions. Let's call them HL. And then we are going to form a linear combination of those basis functions. And our basis functions could be polynomial, could be sine, cosines, give us Fourier, or it could be hat functions giving us finite elements. But here, using neural networks, we want to actually learn our basis. So the idea is, what if you postpone writing down your basis functions? What if you say HL is a linear combination of a bunch of other bases? But then if you forget about this nonlinearity here, everything is going to be very boring and linear. It's going to be WL times WL minus 1. That's gonna, you can call that a new matrix, W tilde. And you can only model linear functions this way. And that's the reason you're introducing a nonlinearity here. It could be tanh, it could be ReLU, it could be Swish activation function, or any other type of activation function or nonlinearity that you like. And this nonlinearity is being applied pointwise. Now you keep doing the same thing, HL minus 1. You postpone it to HL minus 2. And then you keep doing the same thing up until you reach your initial point, X. And then it's going to be a feed-forward neural network. You give it X, you multiply it by W0, you push it through a nonlinearity, you take H1, you do the same thing to it, and then you get f of X. But the idea is now you want to fit this model to your data, and therefore you need to find the best parameters. And we know that a good method is maximum likelihood estimation. And that's what you're going to do. Your model was normal, so you get f of X here. And f of X is going to go in the mean of your normal distribution, and that's going to give you a likelihood. The normal distribution has an exponential term in it. To get rid of the exponential, you take a log. And in machine learning, you usually like to minimize. Therefore, you multiply by a negative sign. And this is what you're going to get in the end. That's your objective function. This was your likelihood. Maximum likelihood is equivalent to minimizing the loss. And this is our loss function. This is in vector notation. If you write it in, if you expand it in terms of your data, you're going to get the familiar mean squared error, assuming that sigma is known. It's a constant. So you have a loss that you're going to minimize with respect to your weights and biases, and it's going to give you the best weight and bias. One cool thing about neural networks, and the reason why they are scalable to big data, is because this N, you don't have to compute this summation over your entire data set. While doing this, while solving this optimization problem, you need to have good estimates for your gradients, the gradients of your loss with respect to W and B. Therefore, you can do your summation over subsamples of your data, over mini batches of your data. So N could be small per each iteration. And then once the parameters are learned, the rest of it is very easy. You just take X star. Somebody gives us X star and wants to know what is the value of F at that new point, which is not part of your training data. You just take X star and push it through your neural network and report the value. But how are we going to make neural networks physics informed? What is the key observation? The key observation is that the derivative of a neural network is a neural network. If you take the derivative of F with respect to X, you're still going to have a neural network. What's going to happen? You're going to do some backpropagation, some chain rule. These W's are going to get transposed. Your activation function, you're going to have the derivatives of your activation function. It's going to be 1 minus tan h squared, for instance, in the case of tan h. But whatever that you do, you're going to end up with a computational graph. So the derivative of a neural network is a neural network. So that's the observation. And the cool thing is that in scientific computing, we have a lot of derivatives. You write down your partial differential equation, you write down your differential equations, etc. Here is an outline of the talk. We are trying to devise a method that can handle small data, medium-sized data, or big data. And it could work with very little assumptions about our physics. some more assumptions. Maybe you know your physics up until some parameters, or it is fully physics-based. So there are usually two arrows. One goes from left to right, the other one goes from right to left. And there is a reason why they are going from right to left. You cannot learn your physics from small data. You have to make more assumptions about your system. That's just the totality. That's there is no free lunch. If you increase the size of data, these types of classes, small data physics-based, let's call them forward problems. The ones in the middle are my favorite. They are inverse problems and data assimilation problems, where you know your physics up until some parameters. Maybe you want to close your system. And then the other part is going to be model discovery. So it's going to be the same framework that we're going to use for all of the spectrums here. And let's start with forward problems. And let's say this is your physics, and you know your physics fully. So this is Berger's equation, and you know even this coefficient in front of your Berger's equation. What we are going to do is we are going to approximate the solution to this partial differential equation by a neural network. This neural network is exactly what I just explained 2 slides ago. So there is nothing special here. It's just exactly what I just described. And this is physics uninformed. There is no physics here. Now let's try to physics inform it. We take the derivative of u with respect to time, the derivative of u with respect to x with respect to x twice, and return f, the residual. F and u have the same parameters, the same weights and biases. And it's this idea of parameter sharing that is really powerful in deep learning in general, and it's going to help us here as well. And what is the definition of being physics informed? Why do we call F physics informed? What is the definition? Any samples that you generate from your weights and biases. So you pick your weights and biases at random. That's going to give you two functions, u and f. This pair of functions are going to satisfy this equation by construction. So this equation is going to hold even if your weights and biases are random. And this is going to hold machine precision accurate. And that's the definition of being physics informed. Now the idea is, how do you get the physics out? For instance, how we're going to use it. Okay, you encoded your physics in F, but how do you take it out? The answer is you are not interested in any F, you are interested in a particular F. For instance, maybe you had a forcing term, or maybe your forcing term is just 0. And that's going to give you your loss function. So you are doing 2 regression. You are doing some regression on your solution. Perhaps you have some data at the boundary. Perhaps you have some initial data. Perhaps you have some data in your domain. Perhaps you have some data on the derivative of your function. So those are going to give you your regression on U. The data on U, TU, XU, and U, this data is given to us by nature. So we have no control over it. Somebody gives us a data and then we have to live with it. But the data here, where you are enforcing your equation to be 0, is under your full control. You can have as many of them as you want. So these are just your scattering points in your space and time. So you can imagine that this summation could go from 1 up until infinity. So you can have infinitely many of those types of data. And why in practice can you have infinitely many of them? Because of the ideas of mini batching, because you don't have to process your infinitely many data at once. You just need to process, I don't know, 250, 256 of them per each iteration of your optimization. And remember, you're optimizing this objective function with respect to your weights and biases. So you turned the problem of solving a partial differential equation into an optimization problem. Once you solve that optimization problem, you can get a solution to your Berger's equation. This is good. From scientific computing perspective, you just created a new algorithm, and you can compare this to finite element, finite volume, finite differencing. But I'm not advocating pins for forward problems, because there is already half a century or more of finite elements, of finite differencing, of a spectral element methods. And when it comes to low dimensional problems and forward problems, basically solving them on complicated geometries, perhaps using finite elements is a better choice, or finite volume is a better choice. But if you look at this problem from machine learning perspective, things are going to become interesting. You are training a deep neural network, which could have thousands, millions, billions, or trillions of parameters using very few data points. And this is the idea of data efficiency. In this case, you are training a neural network with 100 data points.
Maziar, there is also the possibility that obviously in the forward problem, when you have many dimensions, you're just going to be much more efficient with a neural network than with traditional methods.
So yes, that's actually a very good point, and it's actually where I'm going next. Not the next slide, but the slide after.
And also, this is defined from physics department. I'm an astronomer, but I'm wondering whether this, the neural network approach will improve the numerical precision here.
So I'm going to go into more details. If you give me some time, I will go into more details.
Thank you.
And try to answer those questions in their appropriate slide. Okay, so far so good. In the next slide, I'm going to go ahead and introduce a new equation, not because there is anything special about Schrodinger equation, but because it's going to help me explain a little bit more about the cost of pins. The Schrodinger equation is going to have the solution to it. It's going to have a real part and an imaginary part. Let's call them U and V. Let's put a neural network that takes time and X as an input, and it's going to output U and V. This neural network is very boring, so there is nothing special here. And that's why I'm using a gray color there, because it's very boring. It's a linear combination of your input, some activation function, linear combination of your hidden activation functions, and a linear combination of those hidden layers is going to give you, those hidden units is going to give you your U and V. So very boring. And let's say this neural network has a depth of 10. So you have 10 layers. These operations, the red ones are the exciting ones. As soon as you take the derivative of one of your outputs with respect to your input, you're doubling the length of your neural network. So it's going to become twice as deep. So now, after this operation, your neural network is going to be 20 layers deep. After taking the derivative twice, you're going to double the already doubled length. So the length of your neural network is going to become 20. And why do you double? Because you have to backpropagate. So these neural networks are going to get deep and deep, deeper and deeper, depending on how many derivatives you are taking in your differential equation. For instance, something like Koromatov-Sivashinsky equation is going to end up being very deep because you have fourth order derivatives. And that's the computational cost. But then the rest of it is very boring. You just write down your loss function, mean squared error with respect to initial condition, boundary conditions, and the real part and the imaginary part of your equations. The rest of it is optimizing this mean squared error. And as soon as you do that, once the optimization is done, you get a solution to your Schrodinger equation. And this is the absolute value of the solution to Schrodinger. And now I'm going to address the first question that you asked me. Exactly as you mentioned, neural networks, they do not, their degrees of freedom are their weights and biases. So their degrees of freedom are not tied to any underlying grid. So you can think of them as mesh-free. And because they are not tied to any grid, as soon as you go to higher dimensions, you're going to start to see some advantages to neural networks. In higher dimensions, let's say in 1 dimension, you need to put a grid with 10 points. In 2 dimensions, you're going to put a grid with 100 points, 10 squared. In 3 dimensions, it's going to be 10 cubed. And then in 100 dimensions, it's going to be 10 to the power 100. So you run into the curse of dimensionality. And let's say your problem is now solving a high dimensional partial differential equation. Where do they show up? They show up in a stochastic control, and they show up in pricing derivatives, basically options on assets. So asset pricing or derivative pricing. There is this theorem. The theorem is not mine, which tries to relate forward-backward stochastic differential equations and quasi-linear partial differential equations. And the relationship is this. The solution x, y, and z to your forward-backward stochastic differential equation is given by the solution to your partial differential equation. So there is a function that takes you from x to y, and then something nice happens. The derivative of u with respect to x is going to give you z. And just to make sure and convince ourselves that the theorem is at least on a high level making sense, this is your forward dynamics. X could be high dimensional. It could be, for instance, 100 assets. It's a stochastic process. There is some Brownian motion here. There is mu, our drift, and mu is showing up here in our PDE. There is sigma. Sigma is showing up here. And there is phi. Phi is appearing here. And there is G, the final condition, or the terminal condition. It's showing up here. And you have some initial condition for your forward dynamics. So X is forward, Y is backward. So far, so good. So this is not mine. But what is the contribution? As soon as I see a function, I think that it's a good idea to approximate it with a deep neural network. And that's exactly what we're going to do. We're going to say U is a neural network. And we get something for free. The derivatives of U were appearing here. And we know that computing derivatives with respect to the input, we can get them for free. No new parameters are going to get introduced. So this network and the other network are going to share parameters. So you are being parameter efficient. Now, the question is this, okay? You approximated your function with a neural network, but what is your loss function? And what is your data? The data are coming from your Brownian motion, and the Brownian motion, in addition to sigma, mu, and phi, are gonna help you explore your space in a physics-informed fashion. So that's why you don't need to put a mesh or any grid on your domain. Okay, that's one cool thing. You don't need to put a mesh. And what is your loss function? Because in the end, you want to train this and you need to write a loss function. And your loss function is going to come out of discretizing this equation. Basically, you do Euler-Mariomme scheme. And you discretize this. It's going to give you a complicated looking loss function. Mathematically, it's going to fill up the entire slide here. But computationally speaking, it's just a loss function that you can optimize. And that's exactly what we are going to do and solve two types of problems. One of them is Black-Scholes equations in 100 dimensions. And the other one is Hamilton-Jacobi-Bellman equation in 100 dimensions. So what are we going after? You have 100 assets. They have a forward dynamics. And we want to write an option on those 100 assets. This G function that you see here, these are these blue, these black circles, and we know them. Why do we know them? Because whatever that's going to happen in the future, the stock price is either above the threshold that we chose for our option, and our call option is going to have a value. Otherwise, it's going to be 0, and it's not going to get executed, so it's not going to have any value at that point in time where the option expires. But we don't care about the price of the option in the future. We want to trade it today, or maybe tomorrow, or the day after tomorrow. We want to know the fair price for that option. And this square is going to give you the fair price today. So the other competing method, forget about finite difference in finite elements. They are not going to apply to this problem. The other competing methods are Monte Carlo type of methods. And those types of methods are going to give you this square. They are not going to give you the price tomorrow. So you have to recompute your computations that you were doing for Monte Carlo. And then the price the day after tomorrow. They're not going to give you that. But here you're going to get that for free because you're learning your function. You're learning U. And you can evaluate that function wherever you want for whatever time that you want. A similar scenario happens for stochastic control. For stochastic control, U is going to be your value function that you're learning. For your assets, it was the price. Here is the value function. So in high dimensions, you can start to use neural networks. Where else can you start to see advantages to neural networks and pins? It's when you're repeating something. When you are solving an inverse problem. When you're solving your inverse problem, you need to solve your forward problem multiple times. Perhaps not in a Monte Carlo fashion. Perhaps you adjust your weights, adjust your parameters, the parameters of your differential equation slightly, and then solve your PD to the end. And then see how much error you made compared to your data, and then backpropagate that data, that errors, to update the parameters of your PD. So you have to repeat that multiple times, maybe thousands or millions of times. Similarly for data assimilation. And this is exactly my favorite part of this talk. The rest of it is going to be model discovery, but this is the favorite part. Let's see why. And let's start easy. Let's start with two-dimensional Navier-Stokes. And let's say you don't know two parameters, lambda1 and lambda2. And the framework I promised is going to be the same framework as before. So we are going to use a neural network that takes as input 3 variables, and it's going to output 3 other variables. The input variables are time, x, and y. The output variables are going to be u, v, and p. This is your neural network. It's going to have, I don't know, thousands of parameters. And then in addition to those 1,000 parameters, you're adding 2 other parameters. So it's going to be 1,002 parameters that you need to find. Then you're going to write down your F, G, and H. These are your physics-informed neural networks. They have exactly the same number of parameters, 1,002. And F, G, and H are coming out of taking derivatives of u with respect to time. And these you are going to get for free. These are basically automatic differentiation, machine precision accurate. So F, G, and H are physics informed. Now we need to get the physics out. Here you need to have more data. If you give it only boundary condition, because you don't know your physics, you don't know what you're solving for. So boundary conditions are not enough. So you have to give it more data. And let's say you collect data behind the cylinder. And we are collecting data only on u and v, only on the velocity, not on the pressure. So you have absolutely no data on the pressure. Why? Because if you try to measure the pressure inside your fluid, you are interfering with the dynamics of your fluid. If you put any instrument in there, you're going to interfere with the dynamics. So we are going to measure what is measurable. What is the data at this point in time and at this location? This is the txy. You know the corresponding velocity. That's your data, and the data don't have to be on a grid because we know that we don't need a grid for neural networks. So these data could be scattered in a space and time. That's your data. Given the data, you're going to write down your loss function and then optimize that loss function with respect to the parameters of your neural networks and lambda1 and lambda2. And then you're gonna get good estimates of your parameters, even in the presence of noise. So that's good. And to be honest, when we were writing this paper, we were trying to find the Reynolds number, having something to do with the shape of the object in front of us. And some people criticize this work and say, you're learning only 2 parameters, lambda1 and lambda2. And that's not true, because you're learning p as well, and p is a function. And you're putting a neural network on p, so it's a field that you're learning actually, and it could have thousands of parameters on its own.
Yeah, I think this is really amazing, you know, that you can learn the whole field. I mean, to me, this is much more important than learning the parameters. I mean, or even discovering the PD. Well, I mean, discovering the PD, of course, but you know, learning the entire field, to me, is incredible. You know, and by just measuring a scalar, right? Just measuring some kind of a die or something.
So yes, we are not there yet, but we're going to get there by measuring the scalar and using the scalar transport equations. Yeah. Here you have data on u and v. And then we are going to relax that. We are going to say you have data on the concentration of some dye injected in the flow. But where is the pressure coming from? It's coming from these two equations. They're coming from your momentum equations. And as you can see, the pressure is unique up until an additive constant. Why is that? Because this is incompressible Navier-Stokes and only the derivatives of P are showing up in your equation. And as you can see, the scale is off because of the exact same reason. The pressure is unique up until a constant. The pattern is correct, but the scale is off. So this was encouraging that you can actually learn a field. And then we said pressure is important when somebody is having a heart attack and there is a stenosis around an artery around somebody's heart. The doctors are going to look at the pressure drop around those stenosis, and they're going to say how severe this stenosis is. Do we need to do any sorts of operations on that patient? And we said, okay, we need data for it, and let's try to inject particles. And we injected particles, and mathematically, the method is working. It's giving us the pressure pattern is matching. The figure on the left and the figure on the right, they are matching. And computationally, it's working. But it's a very bad idea practically because you cannot inject particles in somebody's arteries. It's going to kill them. But we didn't give up. We said we go to radiologists all the time, and they're injecting dye in our arteries to visualize and qualitatively say there exists a stenosis, there exists an aneurysm. What is that data like? That data is like the concentration of a passive scalar, basically your dye. It's passive because it's not going to interfere with the dynamics of the fluid. It's getting advected by the fluid, and it's diffusing because you have some diffusion constant for the dye. And that diffusion constant, if you non-dimensionalize your equation, is going to give you your Peclet number. We said, okay, let's try to test this idea. Let's say this is your data. Given that data and assuming that you know Navier-Stokes, let's go ahead and try to back calculate the velocity and pressure. But we were predicting the future, and we didn't want the method to be dependent on the geometry. We wanted to have something that is geometry independent. We didn't want the method to depend on boundary conditions or initial conditions. And we wanted to extract all of the data, all of these patterns out of this data, out of concentration only. That's your data. And the method actually worked. So you're going to learn U, V, and the pressure when Peclet number was equal to Reynolds number. We said, what happens if the Peclet number is smaller than the Reynolds number? Basically, your dye is going to diffuse faster. What's going to happen then? We still got the pattern correct. We still got the velocities. And we said, let's increase the Peclet number and see what happens. And this was early success. It was encouraging, and we said, okay, let's go ahead and apply this on a more complex geometry. Let's say this is your geometry. And why did we insist on a method that is boundary condition independent? Why? Because this aneurysm is the aneurysm behind somebody's left eye. It's being cut out of the entire arterial system of a human being. So who knows what are the correct boundary conditions here? Or what are the correct boundary conditions for the aneurysm? The idea is that this concentration should be enough information to give us the velocity field, assuming that you know Navier-Stokes. Let's see what we have from what are the complications. Why is it a hard problem? You have a neural network. It's heavily parameterized, but you have only data on a single component, on a single output. You don't have any data on U, V, W, or P. And for those of you who know neural networks, there is no way to train this and get U, V, and W and P out. You might get C, but you're not going to get U, V, and W and P. And that's why you need to make some assumptions. And these are the assumptions that we make. We assume that the Navier-Stokes equations is a good model. And we assume that we know the equations for the concentration. And from that, you're going to write down a loss function. This loss function here is a regression. So this is very boring. There is nothing special there. But then you're enforcing 5 equations to be 0. And one thing to note is that this data here corresponds to the data to this visualization that you see up there on the right. But the data on your equations, you can have infinitely many of them. So you can just put points in your space and try to enforce your equations. And then after the optimization is done, you're gonna learn the velocity field, the streamlines color-coded by the pressure, and you can learn the shear stress on the wall of the aneurysm. And the shear stress, we are reporting it in the paper. So from this point on, I'm gonna go a little bit faster through a couple of slides because it's gonna be the same framework applied to different problems. One of them is fluid structure interaction. So these are your Navier-Stokes equations. This is your wave equation for your solid. This has applications when you are doing deep sea drilling or you're designing bridges. So you have to take these effects into account, these vortex-induced vibrations. We can compute the lift and drag forces, and at the same time, we can compute the damping coefficient, the stiffness coefficients, and Reynolds number, etc. You can do Eulerian and Lagrangian neural networks. This is exactly the slide that I started with. You inject particles in a flow. This is feasible in external flows, but not internal in human body. And then knowing the Navier-Stokes equation and knowing the ODEs, we can compute the velocity and the pressure. We can do turbulence. For turbulence, no two simulations on any computer, but basically the same computer, if you do your simulations, are not going to give you the same solutions because it's a chaotic system anyways. Tiny perturbations, tiny numerical errors, it's going to give you a different solution. So perhaps a better idea is to learn the underlying distribution for the turbulence model. And the solutions are going to be samples from this probability distribution. So I'm not an expert in turbulence, but the last author here is Peyman. What he has is a paper that takes in 50 pages of rigorous mathematics to take you from P to D. And D is this coefficient here, which is a function, which is a field. To the eyes of our algorithm, it's very similar to before. You have data on P, you don't have any data on D, but you have an equation for it. And this is the equation that they are actually solving in that paper to compute D. For us, it's going to be an optimization problem. Once the optimizer has done its job, you're going to end up with your learned D, which is matching your exact D. Now I have 2 more slides about model discovery. This is my least favorite part of the talk, but the idea is that the same framework is going to enable you to solve those sorts of problems as well. And let's start easy. Let's start with ODEs. You have a finite set of variables. And what you're doing is writing down an equation. This is your ODE. And as soon as I look at that ODE, I see a function, f. And as soon as I see a function, the first thing that comes to my mind is neural networks. Let's approximate that with a neural network. We know what is our data. The data are going to be time series. But what is your loss function? It is very similar to that forward-backward stochastic differential equation. We are going to discretize this equation. And that's going to give us a loss function. So if you take the terms on the right-hand side, take it to the left, do a subtraction, square it, that's going to give you your loss function. Now you can optimize that loss function, minimize it with respect to the parameters of your neural network F, and that's going to give you your learned dynamics. For instance, for Lorentz system, again, it's a chaotic system, so there is no hope for you to get every single trajectory correct, but you can get the big picture correct, like attractors. Or you can do Hopf bifurcation, where you have no dynamics on mu. You have only dynamics on x and y. Or you can do glycolytic oscillator, typical of biological system. Or you can do SIR type models for our COVID era. Or you can do Navier-Stokes when you're using POD to project the dynamics into 3D. Can we actually work with infinite dimensions? Can we actually start to work with PDEs? A generic form for partial differential equations is this, at least the time-dependent ones. You have the derivative of u with respect to time is equal to a function. In the case of burgers, it's going to be u times ux, and then some coefficient uxx. But here it's a function, it's a generic function. There is time, there is x, there is u, and then there is ux, uxx, etc. What are we going to do? The framework, this equation is very general. So u could be a vector. Basically, you can have a system of partial differential equations. And x could be a high dimensional input. So this is a very generic way of writing differential equations, partial differential equations, time dependent. What we're going to do is we are going to approximate u by a neural network. So there is a function that takes time and x as input and outputting u. But then ux, uxx, uxxx, etc., you don't have to worry about them because you can just use automatic differentiation. So these guys you can compute for free. So that's one neural network. There is also another neural network on N, approximating your dynamics. It's very similar to what we did in the previous slide. Now you're going to write down your residual F. This is physics informed, but then you don't know your physics. Your N is a question mark. You don't know your physics. The rest of it is optimization. Let's collect data. Let's collect data from time 0 to time 6.7 of the dynamics of Berger's equation. This is sine function, your initial condition. Now here's the problem setup. You go ahead and train not only U, but also N. As soon as you learn N, you have some equation. So you have the Berger's equation, you have your neural network equation, you have two equations. And now you want to test whether you actually learned anything or no. How can you test it? You can give these two equations the same initial and boundary condition and solve both of them. And that's what we're going to do. We're going to solve both of them. Same initial and boundary condition. From time 0 to time 6.7, where you had data, there is some convincing that you actually learned something, but perhaps not too much because you already know your data and perhaps you are solving a simple regression problem. And we know that machine learning is good at interpolation, so perhaps you are not doing anything there. But from time 6.7 up until time 10, you had no data and the algorithm is extrapolating.
So do you know N here? Do you know the operator N?
That one, this is my last slide. I'm gonna answer questions when we are done. How about that?
Yeah, go ahead. Yes.
So now perhaps a better test is what if you change your initial condition to something totally different than sine function, maybe exponential function. You give these two systems the same initial condition and solve both of them without any training. So the parameters of N are fixed. So you don't do any more training and just testing what's going to happen. And the exact dynamics is matching the learned dynamics. So it's an indication, it's a hard indication actually that you learned something. It's a hard test. There is another result in this paper. It's a failure case, and it's about studying the importance of data for these sorts of model discovery. It goes back to identifiability of dynamical systems. What if this is your training data and you want to test it on the figure above? Just switch the role of these two. What's going to happen? The algorithm is going to fail, but it's not going to fail miserably. You are going to get a shock, but the shock is tilted to the left. And that pattern is being inherited from this dynamic, from this data. So the point is that the data matters. This is a richer dynamic compared to the dynamic from this. The dynamic below is one-sided. The dynamic above is two-sided, and that's why it's giving you a shock. You can do the same thing for KDV, Koromoto-Sivashinsky, Navier-Stokes, etc. And I promise this was my last slide. For most of the topics that I explained, I don't have any proofs. My collaborators are working on proofs. But what I can offer is this GitHub repository. You can just clone it, clone any of these topics that you want, and it should reproduce the results in the papers. And with that, I would like to thank you all and open the floor for questions.
Thank you, Maziar. This was a great talk, full of insights, very didactic. It felt like a lecture, and it was very informative. And I just have a quick comment, and then I'll let others ask questions. You know, the fact that you don't have boundary conditions or initial conditions in the discovering the field from the scalar is really impressive. Don't you run into any kind of well-posedness problems? Like, you know, you have an infinite search space. You don't have any boundary conditions. Is it always possible to recover the correct field, you know?
That one I'm not sure. I have empirical answers.
Yes.
I don't have any mathematical proofs that for the problems that we tried, we were fine.
Yeah,
And,
it's
and
really,
it should be, there should be some mathematical reasons for it. Maybe because this is there is no backward interactions between concentration and U. So concentration is not going to have any effect on U and W and P.
yeah, it's really impressive, and thank you very much. So, any other questions?
I have a question. Hi, Maziar. My name is Ratin Bhattacharya. I'm in the aerospace engineering, mostly work in controls and estimation. But getting very excited about your work on using neural networks to solve PDEs. I tend to use them to do uncertainty quantification, propagate uncertainty, and things like that. My question to you is, most of the work in this area is enforcing boundary condition and the minimizing the residual of the equation. Do you envision any situation when just minimizing residuals may not give the right answer? I mean, I'm not a computational mechanics guy. I just want to kind of get some opinion that if if the residue goes to 10 to the minus 5, is there a situation when I will not get a good answer?
Yes, so that could definitely happen because this is actually a fundamental question. What is 0 on a computer? Is 10 to the power negative 6 0 enough? Or 10 to the power negative 12 is 0 enough? And this is the idea of how much do you want to push your residual towards 0.
But the question, I think, is related to my question, right? I mean, you could have a 0 residue on the physically informed neural network, but you don't get the right answer because you don't have enough boundary conditions.
Yeah, that could happen. But at the same time, it's a very delicate balance between enforcing the boundary conditions and enforcing your equations. So that's not an easy task. I mean, you have to definitely non-dimensionalize your data to put everything on the scale of 1. If the scale of your equations don't match with the scale of your data, you're in trouble.
Also, the collocation points, right, where you're enforcing the PDE.
So that one,
Dense, right? Otherwise, the solution could be in between, in the near measure 0 set of the domain.
actually, that one I'm not really concerned about, these collocation points, because you can have infinitely many of them. So there are some works like hard example mining, which says that look at the curvature of your equation or the curvature of your solution, and then sample more points around that curvature or some other probabilistic method of going around it. I don't worry about it too much because we can enforce these equations practically at infinitely many locations.
Okay, thank you.
So I think it has second or third order effects, which are not, you can ignore them. Because practically you can have infinitely many data.
Mm-hmm.
So Lifan had a question, right, Lifan?
Yeah. So my question is somewhat related with what already being asked. That is, imagine we want to improve numerical precision of a differential equation, and the differential equation may describe physical situations with very sharp jumps in physical quantities. So may not be continuous or smooth. So in that case, we worry a lot about the numerical precision if we want to solve this in a finite element approach. So, that's why, there are other you may either increase the number of pixels or you may try to improve the location of the sampling points. So with the neural network approach, what would be the cost in improving the numerical precision as compared to when we do this in a conventional way of solving these equations? Is there any tremendous gain in that direction?
So I think I'm going to answer your question by going through a slide that I skipped during my talk. This is going to give us some background, and then it's going to help us compare pins to finite elements, for instance. So let's take finite element, finite volume, finite difference. What is going to be your solution space? And how are you going to span it? You're going to choose a set of basis functions, maybe polynomials, maybe hat functions, maybe sines and cosines. So you choose some basis function. How do you span the space of your solution using pins? You're going to put neural networks. So what's the difference here? The degree of freedom for maybe those hat functions in finite elements, they are tied to your grid. So you need to first put a grid on your domain and then put those types of basis functions locally. Here, the degree of freedom are the weights and biases of your neural network. So if you have a very complex dynamics, maybe a chaotic dynamics or a solution that has jumps in it, perhaps going deeper in your neural network or making it wider is going to help you approximate those types of functions. So you need to increase the solution space. And then the rest of it, for operators in finite element or finite volume, etc., you're going to discretize them. Perhaps after writing the weak form, you're going to discretize them. And this is where you're going to sacrifice some of your physics. As soon as you discretize, you're going to sacrifice some physics. Here, with neural networks, you are using automatic differentiation. So you're not going to sacrifice any physics. This is going to be machine precision accurate. But there is no free lunch. You're just postponing your problem. Where are you going to sacrifice your physics if you use pins? This is when you're going to do gradient descent to do your optimization. There is no guarantee that you're going to be able to find that minimum that's going to give you an acceptable residual being 10 to the power negative 12. So this is where you're going to sacrifice your physics. But then the solvers for your differential equations for finite elements are going to be much more efficient. For instance, after you write down your system, you might end up with a linear system of equations that you're going to solve with a linear software. Or you end up with a nonlinear equation that you're going to solve it using iterative schemes, etc. So this is how I would compare pins to finite elements. And I hope it answers your question that if you have a more complex function, you need to use more powerful neural networks. It doesn't have much to do with the points, with your samples, with your collocation points.
Yeah, that's an interesting thing. I mean, I have two questions about this. One is, you know, if you take burgers and you reduce that viscosity, okay, so all the solvers are going to have trouble. They're going to become unstable. Of course, can pins beat traditional solvers as the viscosity goes to zero? You know, that's one big question. And you just said that you just have to have a more complex network. I mean, but it must have to do with training as well, right?
Yes.
I mean,
so these two matter.
Yeah, the loss surface becomes very, very complex, I think, when you don't have enough viscosity. I mean, that diffusion term disappears.
Yes, you are right. Exactly right. Because
Yeah.
that diffusion term matters, and basically you are zeroing it out.
Yeah.
So Maziar, a related question, is the computational complexity across these techniques similar, or is there an advantage to computational complexity for pins?
So finite element, finite volume, finite difference, reduced order models are much faster when it comes to solving forward problems. And what is the bottleneck here? The bottleneck is exactly this gradient descent training. So you have to wait for the training for the optimization to converge.
I'll make a comment here. Is that, you know, once you the pins are highly parallelizable. I mean, you compute this loss on this term, sparse points, and it can be parallelized. So I think that once you go to multiple GPUs and such, it can be faster than the traditional solvers. I have a demo I think I shared with you last night, where, you know, the pin computes the solution faster than a quadrature, you know, of the exact solution. So
yes, if your benchmark, I saw your benchmark is on Berger's equation.
Yeah.
If you are doing Berger's equation, everything works on Berger's equation. So you need to try a harder problem, maybe exactly what you said about Navier-Stokes. Then you're going to see that, yes, finite volume is much faster. And
but Pegasus is still a relevant benchmark, I would say. I mean, it's a very classic benchmark.
Yeah, it's a classic benchmark, but for pins, it's very easy.
It's true.
That benchmark for pins is just very easy.
Which you cannot fault pins for that, right? I mean, it's...
and you had one other comment about...
yeah, the other comment I had was...
oh, I mean, the first one, let me answer that. It was about parallelizable. You're correct. Your neural network, you can parallelize it. But this gradient descent optimization algorithm is an iterative process. So you first find your parameters. So it's an iterative process. It's going to be delta theta. It's going to be theta t plus 1 minus theta t is equal to the gradient of your loss function. And then you have an iterative process over t, over your iterations. And that's slow, and there is no way to parallelize this. I mean, it is what it is. It's an optimization scheme.
Some people do not believe in gradient descent, you know, as your friend Paris, our common friend Paris, he does not believe in gradient descent.
Yeah. But something, when you have massive data and massive neural networks, this is the only option currently.
I see.
And by gradient descent, I mean all of the other.
Yeah, Newton, etc. Newton.
No, I mean Adam or any other
exactly.
type of gradient descent.
Yeah. I mean, but my other question was, in this comparison, I mean, so you said, okay, for forward problems, okay, maybe we are not there yet, but for data simulation, I mean, can you actually do data simulation with traditional solvers? I mean, is that?
Yes, there is actually a huge literature doing inverse and data assimilation.
Okay.
Using, this is the literature of PD constraint optimization.
Ah, okay.
And there are multiple ways to go about it.
Oh, true. I see. You discretize the PDE and solve a linear system or something like that.
But then those are going to be, it's funny. Pins is a much better inverse problem and data assimilation solver problem than a forward problem solver, despite the fact that inverse problems are harder. It's just funny.
Well, I mean, the inverse problem is difficult for everybody, let's say.
Yeah,
so, So maybe for neural networks, it's a little less hard.
So these results, we get them just to give you an estimate of how much time it takes. So when I was running these experiments on a V100 GPU, it would take 48 hours to give me this solution. And that's an inverse problem.
Wow.
If you want to do the same thing, actually solving this problem using Nectar, which is a spectral element solver, the forward one takes more than 48 hours. And imagine that you have to do that multiple times.
Wow.
At least, I don't know, thousands of times to get this. So that's just impractical if you want to go the finite element route or finite volume or spectral elements.
Yeah, that is, yeah, I think that we have a lot to learn still about this inverse problem. For instance, the statistics of it, like how much data you need, consistency, you know, all of this. It interests me a lot. You know, my background is statistical learning.
So that's actually a very good question. So when I was working on this paper, we had a comment from a reviewer who said, can you study the robustness of your method with respect to noise in your data and the resolution in space and time of your data,
right,
of how many data you have?
Exactly.
And then I said, okay, let's do it. At that time, I was at NVIDIA. I had a lot of GPUs in front of me. So I fired 8 GPUs. And I said, I'm going to add noise to this method. And let's say 10% noise is going to kill it at some point.
Right.
But then all of the experiments came out. I was hoping to write the paper and just get rid of the paper. But then none of the results failed.
Oh.
So then I had to increase the noise from 10% to 20%. And I was sure that it's going to fail this time. And it didn't fail. And I kept pushing. And each experiment takes 48 hours. So I had to wait.
Right.
And then around 200% noise, it's going to break the method. So the signal to noise ratio is crazy. And intuitively, why is this happening? Is exactly because of this fact that you can have infinitely many data on your equations.
We can talk offline about this, but you know, the number of collocation points also behaves strangely. I mean, we can talk about this later, yeah. But yeah, I mean, it's not always true that you're going to get a more accurate solution if you have more collocation points. It can be the other way.
That depends on what problem you're solving. If it is
Exactly.
forward, I don't guarantee. If you're doing inverse problem, we can discuss.
Yeah, I'm talking about forward, yeah.
Yeah.
We can discuss, yeah.
So don't use pins for forward, please.
Okay. All right. Any other questions?
Hello, I have a quick one. Do not use pins for forward, but you can still use it for uncertainty quantification. It's kind of part of the data simulation that you were mentioning, the middle part of your two arrows, right? It's not necessarily an inverse problem, but it's you know, uncertainty quantification could fit under data simulation or design optimization and those type of things.
Yes, absolutely. So whenever you have to solve a forward problem multiple times, then you can amortize the cost. And then uncertainty quantification is a perfect example. High dimensional problems is a perfect example. Inverse and data assimilation problems.
The only difference in that case is that the input neuron in your neural net must also include those parameters, I suppose, that you want to modify.
Yeah.
Yeah.
Yeah, absolutely. So
Thank
yeah,
you.
uncertainty quantification, yes, because it has a Monte Carlo type nature. You have to do the same thing multiple times.
So I have a comment that we may discuss later on in the future, is that in astrophysics we have this particular problem of radiative transfer through a very complicated atmosphere, in which some critical parameters are field-like, like the radiation field, the temperature field, the density is a field quantity, and the pressure, etc. And there are also quantities that are very specific to the chemical structures of the atmosphere. Like there could be a sharp boundary between a silicon-rich layer and a carbon-oxygen-rich layer. So, and we involve millions of atomic levels, which all need to be solved through a very complicated network of differential equations. So, this appears to be a very nice place to apply PIN here.
Yep, absolutely. Actually,
Yeah.
the more equations you have, the more PINs is gonna like it.
And we have millions of equations if you want to solve this correctly.
So
So I think that's a very good field.
Yeah.
It's not gonna be easy, but
yeah,
so
there
one
have
thing
been
that
some
I-
papers coming out on pins for radiative transfer. But yeah, it's a very fascinating problem. Yeah. Any other questions? If not, I'm going to thank Maziar. I mean, we already passed our time, and I really want to express my gratitude for him to come and give this talk. And I mean, we learned a lot. I learned a lot, and hopefully we can continue this conversation, Maziar, later. And
no, thank you very much for the invitation, and thank you everybody for being here today.
Thank you,
I appreciate it.
great talk. Thanks.
Thank you. It was a great
bye,
talk.
everybody. Bye, everyone.
Bye.